Good morning, I'm Flavio Esposito, a postdoc researcher at the Department of Engineering of the University of Naples Parthenope. This work was done in collaboration with two units of the National Research Council of Italy, the Institute for Polymers, Composites and Biomaterials and the Institute of Applied Physics Nello Carrara. The aim of the work is the detection of an inflammatory marker, the C-reactive protein or CRP, by using a novel configuration of fiber optic biosensor based on long-period grating. CRP, in fact, is a well-accepted biomarker in clinical use, even if it is non-specific. It is mainly produced by the liver and the concentration in serum, typically around 0.8 microgram per milliliter in a healthy Caucasian person, can increase up to thousands-fold in response to an inflammation process or bacterial infection. Constantly high levels have been also associated to cardiovascular diseases and atherosclerosis. Finally, elevated levels of CRP have been recently found in patients affected by COVID-19. Let's start from the working principle of the long-period grating. It consists of a periodic perturbation of the refractive index and/or the geometry of the optical fiber. The period of the perturbation is of hundreds of micrometers and produces a power coupling between the fundamental core mode and co-propagating cladding modes. As a consequence, by illuminating the fiber with a broadband source, the spectrum of the device presents several attenuation bands associated to different cladding modes. The spectral position is dependent on the grating period and the difference between the effective refractive index of core and cladding modes. These devices find application as sensors and biosensors since the resonance wavelength of the attenuation bands changes under the effect of different parameters, in particular the refractive index of the medium surrounding the fiber. However, the refractive index sensitivity of an LPG in water-like environment, that is typical in biosensing applications, is less than 100 nanometer per refractive index unit. Consequently, proper strategies have been developed to enhance such sensitivity up to thousands nanometer per refractive index unit, as for example by coating with a high refractive index overlay to induce a phenomenon known as mode transition. LPGs can be fabricated by using different techniques. A well-assessed procedure is based on the creation of the periodic perturbation by using an ultraviolet laser through an amplitude mask. Anyway, it can be only applied to photosensitive fibers. There are other fabrication techniques, as for example the electric arc discharge method considered here, that can be applied to all kinds of fibers, including the unconventional type investigated in this work. It is based on the periodic application to the fiber of an electrical discharge occurring between two electrodes, while it is kept under constant pulling tension. The resulting effect is the refractive index modification due to stress relaxation and local tapering of the fiber. In this context, we have recently demonstrated the possibility to induce the mode transition phenomenon in LPGs written in double cladding fibers with W-shaped refractive index profile. This fiber presents an outer cladding with refractive index higher than inner one. The mode field distribution in this fiber is reported in the figure, where it is evident that some cladding modes can be guided in the outer ring-shaped cladding. However, through the etching of the outer cladding, the transition from outer to inner cladding of these modes can be induced, as illustrated in the figure reporting the effective refractive index of fiber modes as function of the fiber diameter. We are interested in working during the transition that is characterized by the highest sensitivity. In particular, the transition is obtained in an all-silica fiber, resulting in a significant enhancement of the refractive index sensitivity and a good visibility of the LPG attenuation bands, with consequent improvement in the wavelength detection. Moreover, the absence of additional coating on the fiber, based on polymers or oxides, may also result in improved stability and possibility of long-term operation. For this work, we selected the single-mode S1310 manufactured by Nufern with pure silica core, fluorine-doped inner cladding and pure silica outer cladding. The LPG was fabricated by using the electric arc discharge technique with a period of 400 micrometers that resulted in the coupling with 5th and 6th order cladding modes, whose spectrum is reported in the figure. After the fabrication, the grating was subjected to wet chemical etching using 24% HF solution at 0.7 micrometer per minute etching rate. The figure below illustrates the resonance wavelengths of the LPG versus fiber diameter during the process. Red shifts can be observed as the diameter is decreased. Moreover, the shift rate is maximum when a modal transition phenomenon occurs. The process was stopped at the mode transition for a cladding diameter around 107 micrometers, resulting in a refractive index sensitivity around 800 nanometer per refractive index unit, that is a 15-fold increase. The spectrum figure shows that main resonance band in water after etching is located around 1560 nanometer with a depth of 15 dB. Finally, the grating was coated with a few nanometer thin layer of graphene oxide, or GO, for the creation of carboxylic functional groups on its surface. The device was dipped in a 2 mg per milliliter graphene oxide solution in water at 100 mm per minute speed. In this case, the main attenuation band was shifted to 1535 nanometers with a depth of 10 dB. In the following, this sample will be named as LPG-B, while another sample was also prepared with slightly lower sensitivity, LPG-A, for comparison. Here, a schematic of the experimental setup for the detection of CRP is reported. The fiber optic sensor is embedded into a microfluidic system. The channel has a dimensions of 40 mm in length and 1 mm square in section and a volume of about 40 microliters. The system is thermally stabilized using Peltier cells and reference sensors. A peristaltic pump is used to flow the liquid from an inlet to an outlet at constant rate. The optical spectrum of the LPG is acquired in real time by using a broadband source and a spectrum analyzer, while a custom LabVIEW software is dedicated to the detection of the resonance wavelength. To attach the receptor for the CRP on the fiber surface, the following immobilization protocol was carried out. The figure illustrates the evolution of the resonance wavelengths of the two samples during the procedure. The GO directly provides the functional groups, which were activated by cross-linking chemistry with ADC NHS for about 30 minutes. The covalent immobilization of the receptor, monoclonal antibody C5, was performed for 1 hour at a very slow flow rate of 15 microliters per minute. The reacted antibodies were removed washing with phosphate buffered saline (PBS) at a faster slow rate. Finally, the surface passivation was obtained with bovine serum albumin (BSA) and washing again in PBS. The last step is useful to prevent non-specific adsorption. Once that bioreceptor immobilization was done, we performed the detection of CRP concentrations within range 0.01–100 micrograms per milliliter in samples of human serum. Analyte binding was done for 20–30 minutes at a slow flow rate of 25 microliters per minute, followed by a washing step with PBS for 10–15 minutes. The response of both LPGs is reported in the figure. Here, the first step refers to a specificity test with a solution of free CRP human serum used as a negative control. After that, the residual wavelength shift, measured after rinsing in PBS, reflects the amount of CRP that binds at each step. The sensor response moved monotonically towards shorter wavelengths with increasing CRP concentration, thus in agreement with the sensing mechanism of the LPG. Finally, the calibration curves of the biosensors were drawn in semi-log scale. The resonance wavelengths have been scaled with respect to the baseline value. For each experimental point, the mean value and associated standard deviation for 20 subsequent measurements are reported. Fitting of the experimental data by using the logistic function expressed in terms of delta lambda is also reported. It was extrapolated from the Hill equation, which is a well-accepted model to consider the degree of interaction between ligand binding sites. A series of parameters of interest can be derived to assess the performance of the biosensors. The limit of detection is one of the most important, and it is defined as the variation of the signal relating to the concentration 0 of the analyte plus 3 times its standard deviation. Here, a very low limit of detection of 0.32 nanogram per milliliter was attained in complex matrix of human serum. Another interesting parameter is the working range of the biosensor, that is defined as the concentration range between 10% and 90% of the dynamic range delta lambda max. In this case, a large working range comprised in 2 nanogram per milliliter up to 100 microgram per milliliter that is clinically relevant was found. To conclude, we have demonstrated a novel fiber optic biosensor based on an LPG written in double cladding fiber and working mode transition, exhibiting both high sensitivity and good visibility of the resonance peak. As the transition is achieved in an all-silica structure, the device has the advantages of stability and long-term operation. As a consequence, we demonstrated the detection of CRP in human serum with a low limit of detection and large working range. Thank you very much for your kind attention and to the organizers for giving me such opportunity.